All right, so today is a huge day because we're going to prove a very important theorem. So we've talked about equivalence relations a lot over the last few lectures. And today we're going to make a formal definition of something we've mentioned several times before, which is a partition. The main theorem that we're going to show today is that there's basically a one-to-one correspondence between partitions and equivalence relations. Given an equivalence relation, that generates a partition. Given a partition, this corresponds to an equivalence relation. This is a very important result that's used in higher mathematics all the time. So let's go ahead. All right, let's start with the definition. Let X be any set. A collection AN of subsets of X is called a partition if two properties are true. The first one is that the set X needs to be the union of all the ANs. Sometimes this is called exhaustive. And the second property is for any M and N, either AM equals AN or AM and AN are disjoint. This is sometimes called the exclusive property. So a partition is sometimes said to be a collection of sets that are exhaustive and exclusive. Let's look at some examples. First example is let's take the set X to just be the numbers 1, 2, 3, 4, 5. Let's let A1 be 1, 3, A2 be 4, 5, and A3 be 2. This is a partition. Notice that all of the sets are disjoint and their union is the whole set X. Here's another example. Let X be the real line. Let AN be the closed interval from n to n plus 1, and consider the collection AN where n ranges over the integers. We actually proved earlier that this is a partition. Here's yet a third example. Let X be the integers. Now choose and fix n. Now consider the following n sets. A0, A1, A2, all the way up to AN minus 1, defined by AR is the set of all integers that are equivalent to R mod n. Turns out this is a partition, and we have proved that in the past. But we'll discuss this particular partition in great detail going forward. Okay, let's dig a little deeper into that example. Let's fix n and consider an equivalence relation on the integers where x relates to y if and only if x equals y mod n, which we know is equivalent to n dividing the difference y minus x. Let's first check that this is an equivalence relation. To check reflexive, just notice that x is equivalent to x mod n, or x minus x is 0, which is divisible by n. To see symmetry, note that if x equals y mod n, then y equals x mod n. Now finally, let's do transitive. Let's assume that x relates to y and y relates to z, which means that y minus x is divisible by n, and z minus y is divisible by n. Let's say yx equals kn and zy equals ln. Well then, z minus x is z minus y plus y minus z, which is kn plus ln, which is k plus l times n. So this is also divisible by n. Since we've established the three properties, this is an equivalence relation. So we might ask, what are the equivalence classes of this relation? Well, it turns out it's exactly the sets we just talked about. The set of all integers that are equivalent to 0 mod n is exactly A0. The set of all integers that's equivalent to 1 mod n is exactly A1, and so forth. So what we see in this particular case is that the equivalence classes for this equivalence relation form a partition. This is a fact that is true in general, and we will discuss it now. We will prove a big theorem in a minute, but first let us prove a lemma. The lemma says that if we have an equivalence relation, then whenever x is equivalent to y, the equivalence class corresponding to x is exactly the same set as the equivalence class corresponding to y. How do we prove this? Well, let's prove this. We're going to prove it directly in both directions. Let's go from left to right. Assume that x is equivalent to y. Now choose any point in the equivalence class corresponding to x. By definition, z is equivalent to x. By assumption, x is equivalent to y. By transitivity, z is equivalent to y, and therefore z is in the equivalence class corresponding to y. Conversely, let z be in the equivalence class corresponding to y. Well, z is equivalent to y because it's in that equivalence class. y is equivalent to x by symmetry, therefore z is equivalent to x by the transitive property, and z is in the equivalence class corresponding to x. Therefore, the equivalence class corresponding to x is exactly equal to the equivalence class corresponding to y. Now let's go the other direction. Let's assume that x and y generate the same equivalence classes. By definition, x is the equivalence class corresponding to x. Since these sets are equal, x is in the equivalence class corresponding to y, and therefore x relates to y. And we're done. Okay, now let's state the big theorem. Let x be any set. If we have an equivalence relation on x, then the equivalence classes of that equivalence relation form a partition. Conversely, let's say that we have a partition of the set x. Then we can define a relation R on x where x relates to y if and only if there is an n such that x and y are both in the same an. Then R is an equivalence relation. Okay, and see what we have to prove there is we've defined a relation, but we have to show it's an equivalence relation. That's the content of the theorem. But you see, when we put these two together, we're really saying that there's this nice one-to-one correspondence between partitions on one hand and equivalence relations on the other. Okay, let's prove the first part of the theorem. Let's assume that we have an equivalence relation on the set X, and now consider the collection of all equivalence classes on the set X. First note that X is in the equivalence class corresponding to X by reflexivity. That means every point X is in some equivalence class. Therefore, the union of the equivalence classes covers the whole set. Now, let X and Y be any 2 points in the set X, and consider the two equivalence classes, one corresponding to X and the other corresponding to Y. What we will now show is that either these two equivalence classes are exactly the same or they are disjoint. How do we prove this? Well, let's assume that they are not disjoint. Let's assume that the equivalence class corresponding to X and the equivalence class corresponding to Y have a non-empty intersection. If they have a non-empty intersection, then something is in there. Let's call it Z. So Z is in the equivalence class corresponding to X and the equivalence class corresponding to Y. What that means is Z is equivalent to X and Z is equivalent to Y. By symmetry, this means X is equivalent to Z and Z is equivalent to Y. By transitivity, that implies that X and Y are equivalent, and by our earlier lemma, this means that the equivalence classes are exactly the same. Now let's prove number 2. Let AN be any partition of X, and define X relates to Y if there exists an N such that both X and Y live in the set AN. Let's first show that this is reflexive. So pick any point X in the set. Because this collection of sets is a partition, that means there is some n such that X is an AN, because remember, the union of the AN covers the whole set. Therefore, X relates to X. Now let's use symmetry. If X relates to Y, then by definition, there exists an n such that X is an AN and Y is an AN. But of course, that means Y is an AN and X is an AN, which means that Y relates to X. Now let us do transitivity. Let X relate to Y and Y relate to Z. So if X relates to Y, that means there's some K such that X is an AK and Y is an AK. If Y relates to Z, there's some L such that Y is an AL and Z is an AL. Notice that Y is both in AK and in AL. But remember that this collection forms a partition. What that means is if these two sets have a non-empty intersection, they must be equal. Therefore, AK exactly equals AL, which means that X, Y, and Z are all in AK or all in AL. They're all in the same set. In particular, that means X and Z are in the same set. Therefore, X relates to Z. We've proved transitivity, and thus we've completed proving the theorem. Again, let me mention, the theorem says that there is this one-to-one correspondence between partitions on one hand and equivalence relations on the other. There's a